Hello, my name is Joanna Ledesma, and I will be presenting a high school topic on angle relationships and connecting them to our current topic of group theory and symmetry, while also extending to an Ehrlichen program perspective. We will hear basic facts at the secondary level, connecting them to our current abstract algebra class, and then extending to the past experiences while making new ones with the Ehrlichen program. In High School Math 2, which consists of algebra and geometry, when students enter the geometry section on parallel lines cut by a transversal, certain angle relationships hold, like corresponding angles are congruent and alternate interior angles are congruent. In the traditional model, students are introduced to angle relationships, given notes, and asked to remember patterns before an exam. While effective for short-term recall, this often turns geometry into memorization rather than understanding. This project shifts that sequence. Instead of beginning with a theorem, we begin with exploration. Students construct parallel lines and a transversal, apply transformations, and observe what stays the same. Through guided investigation, they notice that angle measures and parallelisms remain unchanged under rigid motions. Only after the discovery do they formalize the mathematics. We connect their observations to the Euclidean group E2 and explain angle congruence as a consequence of invariance under isometries. The handout still appears, but now it confirms ideas students have already built themselves. This reframes a familiar high school theorem as an example of geometry emerging from the group action. Klein proposes that every geometry is determined by what he calls a fundamental pair. Here we see the pair as x, g. The first component x is a space itself. This is a geometric setting. For this presentation, we will be looking at the Euclidean plane r squared. The second component g is a group of transformations acting on that space. In Euclidean geometry, the group is E2, the group of rigid motions, known as translations, rotations, and reflections. Geometry is no longer the study of shapes alone when studying Euclidean geometry. It becomes a study of properties that remain invariant under the action of this group. Within this framework, parallelism is no longer just a relationship between lines, it is a structural invariant, something that is preserved by every transformation in E2, and that preservation is exactly what makes a Euclidean geometric property. Instead of focusing on the symmetry group of a single object, we now consider the full Euclidean group of the plane. Euclidean group E2 equal to the semi-direct product of the orthogonal group with the translation group. This decomposition reflects the structure of Euclidean isometries, that every rigid motion can be expressed as a rotation or reflection composed by translation. Because these transformations preserve distance and angle measure, they determine the Euclidean invariance. This includes parallelism. Making this exact, we say a group action here on the line L that for every G in E2, G times L equal G of L. This action on the plane and its lines formalizes what it means for geometry in the form of symmetry. Properties that remain fixed under this action are the exact geometric properties of Euclidean space. Let's look at parallelism through the lens of a group action. Two lines are parallel in the Euclidean plane if they do not intersect. The Euclidean group E2 acts on the set of lines by sending each line to its image under a rigid motion. This key statement is this: if two lines are parallel, then their image under any element of E2 remain parallel. Why? Because isometry preserves distance. Parallel lines remain constant separation, and constant separation implies that the lines do not intersect. Therefore, parallelism is preserved under every transformation in E2. In the language of Klein's Ehrlichen program, this means that parallelism is an invariant under the Euclidean group, and that is precisely why it qualifies as a Euclidean geometric property. On the right side of the screen, we can see two sets of parallel lines. On the top, I've indicated an arbitrary element, G and E2, representing a rigid motion of the plane. On the rightmost set of parallel lines, we see the same lines under the rotational transformation. Notice that although the orientation has changed, the lines remain parallel. This is not a coincidence. It follows of the fact that isometries preserves distance and direction. Therefore, parallelism is invariant under the action of the Euclidean group. In Klein's framework, parallelism is invariant, which is exactly what makes the Euclidean geometry property. Parallelism is not an axiom imposed on the plane. It is the structural coincidence of the symmetry group defining Euclidean geometry. Traditionally, students memorize corresponding angles and alternate interior angles are congruent when parallel lines are cut by a transversal. From a group theoretic perspective, we look at structure that lies within this configuration, which contains symmetry. Because the lines are parallel, there exists a translation in the Euclidean group that maps one intersection plane to the other. Translations are isometries, and isometries preserves angle measures. Therefore, the image of angle alpha under the translation is exactly the same measure angle beta. These angles are referred to as corresponding angles. So what we're really saying about the pair of corresponding angles is that T of alpha is equal to beta, implies angle alpha equals angle beta. This shows that corresponding angle congruence is not just a rule, but instead a consequence of invariance under the action of E2. Now that we have established that angle measures and parallelisms are invariant under the action of the E2, I created a classroom investigation of the exact concept where students work in groups on a hands-on activity in GeoGebra. The lesson begins with ensuring all students are ready to participate in the group activity by knowing and accepting their group role. Tape captains ensure that each member understands how to manipulate the diagram. The recorder makes sure everyone is recording and sharing their findings. The resource manager ensures that everyone is listening and challenges what they hear. Finally, the facilitator checks that everyone is ready at all times to explain concepts and ideas. These roles are set in place to equally challenge each member of the group to participate, listen, speak, and record ideas. This task was created as a booklet within GeoGebra with 7 exploration activities. They first began exploring the tools within GeoGebra, then log down some notes. Once they understand the tools, they're ready to construct their space. Right now, we're not proving anything. We're building the world in which mathematics lives. They create 2 parallel lines, L1 and L2, and transversal T. They use the angle measuring tool to notice and wonder why certain angles might be the same size. They have a few follow-up conceptual questions that they interpret and discuss together as a group. Once they're ready, they create their group response. Moving to the next activity, they are introduced to the space by naming the angle location and see what happens when they move the space. Their space is the plane, x equals r squared. Everything that follows happens inside this plane. Students first explore this freely. They've created the lines themselves and defined the configuration before any group action acts on it. Nothing transformational yet, just structure. Then, applying elements of the Euclidean group, more specifically translations, they map one intersection point to the other. Now we have introduced the group. Through this group action, students observe that angle measure and parallelism remain invariant. We let G equal E2, the group of isometries. This slider applies a translation. This is an element T and E2. Watch what happens to angle alpha. We're mapping one intersection point to another. Now notice something subtle. Even though the entire configuration is moving, the angle measure is not changing. The size stays fixed. This is invariant. Now, apply rotation. Rotate slowly. The transversal changes orientation. The line shifts, but again, angle measure remains unchanged. I could even change the separation between the lines. This changes the geometry of the picture, but it does not change the equality of corresponding or alternate interior angles. This is a key idea. The transformation changes position, but preserves structure. And the same is applied to alternate exterior angles. We are watching a group action on a geometric configuration, and what survives the action is the invariant. Now students are ready to formalize what they've observed. We're no longer experimenting. We are articulating. To assess their understanding, they must be able to do more than just state the theorem. In this modeled example, I demonstrate by stating, let L1 and L2 be parallel lines cut by a transversal. Let alpha and beta be corresponding angles. As a visual learner, I like to draw a diagram to go along with my thoughts. My parallel lines, my transversal T, my intersections, alpha, and beta. We first need to define an element where the transformation is T and E2 as a translation mapping one intersection point to another. Since translations are isometries, we know the angle measures are preserved. Thus, T of alpha equals beta. This means that the measure of T of alpha equals the measure of angle alpha. But we know T of alpha equals beta. So, the measure of angle beta equals the measure of angle alpha. The angle measures are equal to each other. Notice the structure identifies transformations, states isometry, invokes invariance, and concludes equality. This is no longer a memorized theorem. It is a consequence of the group action. Therefore, isometries preserve angle measure. That means we're ready to state corresponding angles are congruent. Now students are ready to give it a try. Here's the task. Given alternate interior angles alpha and beta, 1. Identify a transformation T in E2. 2. Explain why T is an isometry. 3. Use invariance to justify angle equality. And 4. State the invariant property. What I'm assessing is not whether they remember the theorem. I'm assessing whether they can reason through group action. In this way, the assessment measures structural reasoning, not memorization. They're studying symmetry. Now, to fully appreciate the Ehrlichen framework, we compare Euclidean geometry with projective geometry. In Euclidean geometry, the transformation group is E2, and parallelism is invariant under that group. In projective geometry, however, the transformation group is PGL 3R, which is much larger. In projective space, all lines intersect. Parallel lines meet at a point infinity. Because projective transformations cannot finite point to point at infinity, the distinction between parallel and intersecting lines are not preserved. Thus, parallelism is not invariant under PGL 3R. This is the exact illustration of plain central insight. The significance of invariance under transformation groups extends far beyond the classroom. The architecture and engineering structure alignment must remain invariant under rigor motions. Rotations and blueprints does not alter parallel support beams. In robotics, movements is modeled as compositions of isometries in E2 or E3. Path planning depends on preserving spatial invariants such as distance and orientation. Across these fields, the same principles hold. Practical systems rely on geometric properties that remain invariant under transformational groups. In the spirit of the Ehrlichen program, parallelism is not just a geometric relation, it is invariant under the action of the Euclidean group. What used to be a familiar high school theorem became transformed into symmetry theory under the lens of Felix Klein. The structure is simple. A space X, a group G acting on that space, and the properties that remain invariant under that action. Geometry then is nothing more and nothing less than the study of those invariants. Change the group and you change the geometry.